Hey guys, so this video is all about analyzing continuity from a graph. So in calculus, continuity is a really big idea that we're going to spend a lot of time on. So what we really need to know is that continuous really just means that a function is connected. Okay, and you can remember it because they both start with C-O-N, all right? So continuous and connected. I think a lot of you probably already know the word continuous anyway, but that's a way to remember it just in case. Really what it means in terms of calculus then is that the limit as x approaches a from the left of f of x equals the limit as x approaches a from the right of f of x, which we know if we just have those two pieces that a limit exists. But we have to go one step further now and say that that actually equals the function value, which is f of a. So when we look at this graph, we can draw this completely without picking up our pen at all. Any point that we pick, the left limit is going to equal the right limit, which is going to equal the function value. We also have to talk about discontinuity then. So not every function is continuous. If a function has a place where it is not continuous, we say that it has a discontinuity. At that specific x value. So really what we're saying is that somewhere it's disconnected. And we're going to talk about those different kinds of discontinuities that we can have. But even just looking over at this graph, we can see that right here at x naught, at x0, there's a discontinuity. It jumps from here to here. So we have a discontinuity at x equals x naught. And the intervals of continuity just means, well, where is it continuous? We have a break, but where is the function actually continuous? So in this case, it's continuous from here, and it keeps going. The only time it's a problem is at x naught. So our intervals of continuity would be negative infinity to x naught, union with x naught to positive infinity. In other words, it's continuous everywhere except at x equals 0. That's why we have this breaking point here. Okay, so we have four major types of discontinuity that we talk about. This first one is called a jump discontinuity. So when we look at it, we know most of the time, and you guys are already pretty familiar with this idea, but if we have a jump discontinuity, it's probably a piecewise function. And somewhere the breaking point, they weren't equal to each other. So when we look at this jump discontinuity, we can clearly see they're not connected. We can also see that really the limit as x approaches c from the left of f of x is not equal to the limit as x approaches c from the right of f of x. As we're going this way from the right and this way from the left, those two values don't equal each other. So once we get that two of these things don't equal each other, we don't even have to check the third one. Okay? This big idea right here, the left limit equals the right limit equals the function value. That's what we're going to be checking every time we're checking for a discontinuity. Now let's look at the infinite discontinuity. So you guys probably already can look at that and say, oh, well, this right here, that's an asymptote. So infinite discontinuity is just a fancy way of saying asymptote, okay? When we look at this one, we can actually see that these limits do equal each other, but there's no function value right there. So I'm going to call this c, so we can continue to use c. But when we look at it, this limit overall does exist. So the limit as x approaches c of f of x, h of x. This says h of x right here. that limit is infinity, so that's cool. However, the function value, there is no h of c because it's an asymptote, so we can't actually plug in whatever this c value is, which means there's a discontinuity. The next one, a removable discontinuity, hey, that's just a fancy way of saying there's a hole, guys. When we look at this, we can clearly see there's a hole. It's filled in down here. However, because of that hole, that's a problem. Now, when we look at the left limit and the right limit, they equal each other. So that's good. The limit as x approaches c of f of x does exist. So we don't have to do the left and the right limits because we can see by looking at it that they're equal. But the limit does not equal the function value, does not equal f of c because the closed dot is down here. All right. And this last one is called an oscillating discontinuity. So this happens when we have trigonometric functions. So when we look at this one, as we're approaching, this is actually 0, right? So as x is approaching 0 from the left, it's just bouncing back and forth a bunch. As it's approaching from the right, it's just bouncing back and forth a bunch, which means these limits do not equal each other. So the limit as x approaches 0 from the left of f of x does not equal the limit as x approaches 0 from the right of f of x. So sometimes we have to worry about the two-sided limits, especially with like the piecewise and the trigonometric functions. But when we've got asymptotes or holes, a lot of times the overall limit will already exist. It's just that it doesn't equal the function value. All right, so that's the big idea that we're looking at here. So we're going to do just a couple of examples really quick. So this first one, locate and classify the discontinuities on the following graphs, then list the intervals of continuity. So we're just going to focus on this one first. But if we look at it, we can see that there is definitely a discontinuity right here at -1. So the very first one we're going to list is x equals -1. All right, and when we look at that, we can see that that is a jump discontinuity. So at x equals -1, we have a jump. And really what that means is that the limit as x approaches -1 from the left of f of x doesn't equal the limit as x approaches -1 from the right of f of x. As we're approaching from the left, we're approaching 3. As we approach from the right, we're approaching 1, or a little bit less than 1, sorry. So those limits are not equal to each other. All right, then we can also see at 0 that there's a little bit of a problem. On the left side of 0, we're approaching positive infinity, but on the right side of 0, we're actually approaching 3. So we definitely have a problem at x equals 0. And that one is an infinite discontinuity. Oops. If Miss J could spell, that would help, wouldn't it, guys? How about infinite, Miss J? There we go. So there's an infinite discontinuity at x equals 0. And as I said, when we look at it, the limit as x approaches 0 from the left of f of x, well, that's infinity. So that doesn't equal the limit as x approaches 0 from the right, which we know is 3. It also doesn't equal the function value, but we can actually just stop with these two because once it's broken one of the rules, it doesn't matter if it matches one of the others. Okay, this is like an all or nothing thing. We've got one more problem here. There is a removable discontinuity at x equals 1. So at x equals 1, we see that hole. We know it's removable, which means our overall limit does exist, which is nice. So the limit as x approaches 1 of f of x, we can see that that's clearly approaching 1, but the problem is that doesn't equal the function value at 1, because the function value at 1 is actually 2. All right. Now we have to name our intervals of continuity. So I'm going to start over here, and I can see that this arrow is going on for forever towards negative infinity. So from negative infinity all the way up to -1, we're continuous. So from negative infinity to -1. And because -1 is closed, we're actually going to put a bracket instead of a parenthesis. Oh, it might help if you could see it. I'm so sorry, you guys. So negative infinity to -1 with a closed bracket. That is where we're continuous here. Okay. Then let's look at the next chunk. Well, from -1, we have an open circle, and then we're approaching infinity, and we're approaching an x value of 0, which means that one is actually -1 to 0, and both of those are going to have parentheses because they are not included. And we do need to put a u in between here to hold these together. That means union. And then we have an open circle at 0, and then we travel down to this open circle at 1. So that means 3 to 1. I'm sorry, not 3, 0. I'm making a lot of mistakes, you guys. I'm sorry. I don't feel well, so please bear with me. This is from 0 to 1, and they are both parentheses because they are not included in our domain. And then we have one more that we need to look at. And so we have one last patch, which starts at 1 and then goes for forever towards infinity. But again, 1 is an open circle, which means it's going to be a parenthesis, and then we're going off to positive infinity. Okay? All right, let's see if I can do this next one without making any mistakes. I'm so sorry, guys. Bear with me. All right, so for this next one, when we look for these discontinuities, the first place that I see a problem is at -3. So at x equals -3, I see a jump, which means the limit as we approach from the left does not equal the limit as we approach from the right. So limit as x approaches -3 from the left of f of x does not equal the limit as x approaches -3 from the right of f of x. All right, and then I notice that there is an asymptote right here at -1. That means at x equals -1, we have an infinite discontinuity, which means that even though they're both going up to positive infinity, so the overall limit exists, it doesn't equal the function value. We can't have a function value if we have an asymptote there, or at least not in this particular case. So the limit as x approaches -1 of f of x, although it exists, it doesn't equal the function value at -1. All right, and then we have one more. We have another hole right here, or a hole on this one. We didn't have it on this one already. At x equals 2, we have a removable discontinuity, which means that the limit exists, because if we look at this, approaching from the left and the right, we're approaching that hole, but it's filled in down here. So the limit as x approaches 2 of f of x doesn't equal the function value, which is f of 2. All right, and then the last thing we're going to do is those intervals of continuity again. So take a look at your graph. Always start from the left. So this, even though it doesn't have an arrow, it is implied that it's going on for forever. So this is going off to -infinity, and we're good, we're good, we're good, we're good, we're good, all the way up until we get to this open circle right here. So from -infinity to -3, we have some continuity. All right. Then for the next piece, let's go back up to our graph. And we have a closed circle at -3. And then we're good, we're good, we're good. And then, uh-oh, we have an asymptote. which means we're good from -3 to -1. All right, and the -1 is not included because we're shooting up to infinity. And then the next piece is coming down from infinity, and then it's good, it's good, it's good. And we're good all the way up until we get to this hole over here, which means we're good all the way from -1 to +2. So from -1 to +2, and both of those are parentheses because those values are not included. And then we have one more. I'm going to put the U here, and I'll put the piece underneath it, sorry. So we start at this open circle of 2, and then we are going off okay for the rest of the time. So this last piece is going to then be 2 to infinity. So your intervals of continuity just mean, hey, where don't you have problems? And if we look, any place that we named a discontinuity, that's where we have a break in our intervals of continuity. That would make sense, right? We're continuous from -8 to -3. Oh, at -3, there's a jump. Then we're continuous from -3 to -1. Oh, at -1, there's an infinite discontinuity. And then we're good from -1 to 2. Oh, well, at 2, there's a removable discontinuity. So they're definitely connected to each other. You should be able to, once you identify what they are, those intervals of continuity shouldn't be too bad to identify. I hope that all of this made sense. I know it was kind of a lot, and I'm sorry that I sound funny. As I said, I don't feel well. So hopefully you guys got a lot out of this. We can definitely talk on Monday when we're in class, okay? I'll see you guys later. Bye.